Yes, sir, it is started.
Okay, thank you, Gaurav. Sorry for the inconvenience, sir.
Thank you. No problem.
Okay, so good morning, everyone. Welcome once again, all the participants, to this 5 days ATAL FDP on smart manufacturing scope and challenges in research from 17 to 21st of January 2022. I heartily welcome our today's speaker, Dr. Triveni Roy, sir. Before handing over the session to sir, I would like to give the brief introduction of sir to the audience. Dr. Triveni Roy is currently working as an assistant professor in the Department of Mechanical Engineering at BITS Lani campus. He is also a visiting academic at London South Bank University, United Kingdom. Prior to joining BITS Pilani, he had spent close to 2 years at Imperial College London as a research associate and was involved in an Innovate UK project, Wiser Batteries, where he worked on multi-scale modeling to predict the performance of ionic liquid-based supercapacitors that are to be integrated with lithium-ion batteries in developing the next generation of electric vehicles. Dr. Roy completed his PhD from Bhabha Atomic Research Center, Mumbai, under the aegis of Homi Bhabha National Institute in the field of micro manufacturing. He has published his research work in numerous peer-reviewed journals and conferences. His research interest includes manufacturing, energy storage, machine learning, and multi-scale modeling. Dr. Roy hails from Assam, India. So today, Sir is going to give talk on advances in manufacturing, introduction, and research scopes. So now I would like to hand over the session to Sir. Over to you.
Thank you, Tamang sir, for the very brief introduction, and also thanks for giving me this opportunity to give a talk to your FDP, your Atal FDP. So today I'll be taking up two sessions. First one is, as the title suggests, Advances in Manufacturing, Introduction Research Scope. So I thought that this is a very apt title considering the fact that manufacturing has moved on from conventional type of machining process we study in our basic engineering degree, where we have the conventional processes like turning, milling, drilling, and then we had the advanced machining processes which arose based on some certain criteria we will discuss. And then after the evolution of advanced machining processes, we also moved into the field of micro nano manufacturing. And as we start moving from conventional to advanced machining to further lower down, where we are removing materials in the order of cluster of atoms, somewhere down the line, the physics that is involved, that is the mechanism by which material is being removed from conventional to advanced to micro nano manufacturing, becomes difficult to interpret, solely because we do not understand, if we are trying to remove cluster of atoms, what is the mechanism. So these things I will be discussing, and there is a next session as well, where our group currently works on something called as molecular dynamics simulation. So this is a bit different from the finite element, finite difference, and finite volume method that we generally study in engineering, or to some extent in master degree. So that I thought that probably a hands-on session on how to start. So starting any software or learning any software is very challenging. So I thought that probably one session, which will be given by one of the research scholars at BITS Pilani. So he will be introducing the participants on how to install, how to run a simulation, and how the code exactly looks like. So we'll be also carrying out one or two examples based on that open source software. Now moving on to today's first topic, that is advances in manufacturing. So my talk, the overview would be basic introduction about this, then the evolution of advanced machining processes, though I would not go deep into each and every process, just an overview. Micro nano manufacturing, again in very brief, so that we do not spend much time on whatever is already available in the literature. Then something I want to introduce, so that if I'm talking about what are the research scopes currently in manufacturing, understanding the basics of the evolving manufacturing processes, in particular material removal processes, why is it important and how can it help researchers who wants to move or who wants to start their career in this area, what are the things they can expect. Currently, one of the work that we have done using an open source, using molecular dynamics simulation, is on nanopolishing, which I will give a very brief overview of it, and some other areas our group also explores apart from manufacturing. What are the things we generally explore? Now, moving on, when I talk about advances in manufacturing, say for example, I want to know from the participants, anyone can speak up. If I say that my manufacturing advances or advances in material removal processes, I keep on advancing. Now, what is the final stage? When I say that, okay, fine, I have done what is best in any material removal process. Can anyone tell me what do you think would be the minimum amount of material removal which we have control over? Or what can be the minimum amount of material that can be removed so that we can say that we have reached the end point of manufacturing? Anyone from the audience?
So rapid prototyping, sir, or additive manufacturing?
Additive manufacturing, okay, fine. So just let me give you a basic idea of how material removal, material addition, and material kind of forming and other stuffs are different. There is one particular area which is called top down process. When I say top down, I start with the raw material, I start removing material, and I end up to the final product. That is a top down, which is material removal. When I say bottom up, I start doing a layer by layer deposition, and I start from bottom and I reach the entire product. So that is a bottom up, where rapid prototyping, 3D printing, additive manufacturing. Apart from that, you have physical vapor deposition, chemical vapor deposition, a lot of other stuff. Now the question is, I'm talking about a material removal process. I am removing material. What do you think would be the ultimate goal of any manufacturing, particularly material removal? What is the amount of material removal you think would be the end goal? Any idea about it? Anyone? What can be the minimum amount of material removal that can be removed? Ideally, maybe impractical, but what can be the minimum amount of material removal that can be done in any material removal process? Anyone? Okay, fine. Now, let me just move on and explain. Now, what happens is whenever we start removing material in conventional machining process, say we are doing a turning operation, what we do, we remove chunk amount of material. We do not have, number one, control over the process. Number two, the amount of material varies with each pass. It depends on the type of material. So material removal, amount of material removal will vary from point to point. Now we start, when we discuss about advances in manufacturing, we look at improved manufacturing process, and then when we go to narrow down, we move into micro nano, we are removing lesser and lesser amount of material. Now if you look at the atomic structure of any, say, metal, any crystalline thing, we are trying to remove bulk of material which contains large number of atoms. Now when we move into the micro manufacturing or micro domain of material removal, we narrow it down, or the material removal occurs in micrometer cube. Now when we do nano machining, like I'll give you some examples along these slides, we remove material in the form of cluster of atoms. That means a handful number of atoms are being removed. Now what we are gaining when we are converting from turning operation to advanced machining to nano is we are having a much more control on the amount of material we are removing. Now ideally, the utmost control you can have if you want to pinpoint the amount of material removal is when you can remove a single atom from any surface. Say, is just showing the dimensions of an atom and the distance between atoms and average dimension. This is an ideal case. Your actual surface would always be like this. You have some waviness, you have some roughness. So these are very basic terminologies we generally study. Now, this surface may look like this. Our goal in material removal process is to make sure that the whatever the requirement from the designer is, say for example manufacturing a 40mm shaft, so we need to manufacture 40mm, but at the same time depending on the type of machining process you are utilizing, you may have some variation, which we call tolerance, that is generally provided 40 plus minus say 0.3 millimeter. Now, as you keep moving down, removing lower amount of material, you are having much more control. Now, if you just let me open up the pointer. If you look at it, now say for example, I want a very smooth surface, a very atomically flat surface. What I need to do, I need to remove this atom, and these 4-5 atoms, such that I am getting an atomically flat surface. So if you have control, or you are developing a process where you have control on the number of atoms you are removing for each cutting or each pass, you are able to generate an atomically flat surface. So this is something which we can call as an ideal. It may be difficult in the long run to remove only a single atom. However, if we can remove cluster of atoms at locations which we require, that is also very close to ideal. So that is what advances in manufacturing, or particularly material removal, is all about. Now moving on, this is a very simple figure. So there is something blackish here, and there is a small hole here. Can anyone tell me what this particular thing is, this black thing that you are seeing, what this can be? And there's a hole in it. Anything that you can think of, like what can this be? Anyone? Any guesses? What can this be? Okay, let me just put it. So this is actually human hair. So human hair generally ranges from 70 micrometer to 100 micrometer. So what we did, we drilled a 50 micrometer hole in a human hair. So this is the kind of precision and accuracy with which manufacturing has moved into. So imagine you just, pull out one of your hairs. You cannot even see it with a naked eye. What is the thickness? So you need a microscope to just look at it. Now forget about cutting it. If you can actually drill this, that is the extent of what manufacturing advances has progressed into. Now this is just a simple example of how far manufacturing has progressed. Now we are still evolving. It's not that we have reached and there is something that we are stopping here. No, we are still moving ahead. Then this is a SS wafer, stainless steel wafer, and you can see it's formed a mirror image. So this has been done using something called as a nano finishing or a nano polishing process. There are multiple processes available. So you can clearly see that it is more like a metallic mirror, where you can see the image very clearly. So it's not a normal mirror, it's a metal polished or an alloy polished, which gives a very high surface finish so that a mirror image of any object is possible. So this is polishing. Next one, if you look at it, you see it resembles a tool post. It has a cutting tool, but the machine surface is like a mirror. If you talk about turning operation or a facing operation, getting this sort of mirror finish on a metal or on an alloy is next to impossible. Now, looking at it, it still resembles conventional lathe. However, there has been a lot of R&D going into it, and it has become something called as an ultra precision machining process. Cutting tool is not the conventional ones. It is a single crystal diamond. So diamond, as we know, is one of the hardest material known. Based on this concept, the workpiece can give an atomically flat or a very high surface finish, close to 10 nanometer of surface finish. So this is another area where progression has been done from conventional lathe to something called as ultra precision diamond turning. Probably one of the previous speakers, Dr. Rohit, is mostly involved in this. Now these are some of the areas where manufacturing advances has moved into. Now the question is, why do we need to do this? Until and unless there is a need for certain things to be done, we don't require this. Now there has been a lot of applications based on which these sort of advances are being done. For example, if you look at your cell phones, the one that we are using 5 years back and the one that we are using now, the amount of memory, the amount of capacity, and the amount of functionality it has been produced, and the miniaturization that has gone. That means all the components, the chips, everything is getting smaller day by day. This is only because manufacturing has advanced to such an extreme level. Now, apart from that, I'm just showing some basic day-to-day examples where manufacturing plays a key role. For example, this pavement, your shoes, this pen, they all have some sort of manufacturing excellence due to which we are able to use it in our day-to-day life. Now, not only day-to-day life, there are again some advanced applications such as super hydrophobic surfaces. Imagine there is a high rainfall in your area and you're driving your car. Now suddenly your wiper is not working. So if your glasses are super hydrophobic, indicating that whatever droplet or whatever rainfall is falling onto it, it is getting repelled automatically. So the need for wiper is removed. So that can be one of the best possible scenario where you don't need to worry about rainfall and you can have a clear visibility. So that stems from the area of something called a super hydrophobic surfaces. Again, manufacturing plays a key role here. Drug delivery. Now, if you look at the syringes we use, we do have or do experience some kind of niggle or a bit of pain while we are being injected. Now, some kind of research is also being kind of moving ahead where we are trying for drug delivery without pain, where we try to develop some sort of surface patterned polymeric delivery of drugs. So that would be pain-free. So research is also going here. Also, when we do our typical milling, drilling, turning operations, we try to enhance the tool life. So one of the ways of enhancing which researchers are currently carrying out is if we can make some small patterns on the tool so that the lubricant retention is more. That is also one area. Apart from that, there are many more areas where manufacturing advances or evolution of all these high-end manufacturing applications are playing a key role. Talk about aerospace, talk about defense, talk about any other sector, nuclear reactors, any other sector, you would see that the need for manufacturing is growing day by day. That's why every day you see more number of research papers trying to evolve with a manufacturing process which is having some advantages of particular application. So that way, based on applications, manufacturing is getting advanced. Now, evolution of advanced machining processes. So what I have explained mostly about the introduction is how it has evolved. Now, also I've said it's because of applications. Now the question is, was it required? Can't we do this with the conventional processes that we have? Like, we already have a casting process, which is conventionally used across all large scale production. Machining process where we can remove material and we get the desired shape and size based on shaping, turning, drilling and milling, which we generally have in all the workshop across the world. We have a forming process and we have a welding process. So the question is, aren't this enough that we need to go for advanced machining processes? What were the limitations based on which we had to adopt some alternate form of processes which is different from whatever is being shown in this particular slide? Now comes the type of engineering materials. Now I have just given very shortly in 3 verticals: metals and alloys, ceramics, plastics and composites, and there are many others. So you have metal matrix composites, you have recently the evolution of high entropy alloys. So lot other materials which becomes a bit difficult based on the type of properties they have. Using conventional machining process for cutting or removing material becomes a bit difficult. Why? Because of superior properties of the newly growing area of material science. Now, always remember, it's not only the machining process that is being evolved. Day in, day out, a large number of materials are also being fabricated in the lab or going into the commercial production. Now, shaping those materials, the newer materials, in order to use it for particular application is also equally important. So that is one area where material science researchers are currently doing their work. Now, once the material is proven, now we need to make sure how we can shape that material to be used in a particular application. Now, I have divided this into 4 verticals. Ultra high strength. If you look at some of the recently developed materials, one of the key areas would be ultra high strength, high hardness, very difficult to scratch, high temperature resistance, and difficult to machine materials. Now, one of the key factors of conventional machining process, or for example, I'm just speaking about turning operation, is the hardness difference between a cutting tool and the workpiece. If you talk about a copper or an aluminium, it is very easy to be machined using a simple turning operation. Now, once I start increasing the hardness of the workpiece, what happens is there is a high tool wear. I think you all must agree to this. Once the workpiece material hardness starts increasing and becomes very close or even more than the tool material hardness, what would happen? Machining would be difficult and higher tool wear is possible. So therefore, due to these reasons where superior properties of materials as well as the difference in hardness between workpiece and tool material becoming narrow, and certain other product requirements, for example, complex shapes. So it is not always possible to use the conventional processes such as casting, forming, welding, and machining process to develop complex shapes as required by the designer. Machining in inaccessible areas. Now, mostly using a cutting tool, and if you're using a CNC to some extent, we have a 4 axis or 5 axis milling, drilling, turning, whatever. Still, it becomes difficult sometimes to machine some inaccessible areas with control over the amount of material that is to be removed. Stringent tolerances. Now, once production goes and the number of defectives in an industry is to reduce, and we are moving towards Six Sigma processes, the number of defective items has to be reduced. And also, because the market is so competitive for any product, tolerances has to be very, very stringent. That means we cannot allow the deviation from the basic dimension to be very high. So more and more accurate, more and more precise with stringent tolerances becomes a bit difficult using a simple the turning operation or a milling operation. The reason is the cutting tool has their own signatures like the nose radius and other things. Now, if we do not control the amount of material removal, we are not able to provide or manufacture goods which are very stringent tolerances in terms of, and also in terms of accuracy and precision. Better surface integrity. Even if we are able to develop materials using any conventional process, we have to make sure that there are no voids, cracks, subsurface damages, has a better surface integrity, which becomes a bit difficult using conventional process. High surface finish. Now, even if we are using conventional processes like welding for joining, we still need to make sure that, or we still need to add another post-processing operation in order to get a high surface finish. Now, the reason why metal additive manufacturing, the research is still not attaining a proper level of acceptance is because with every metal 3D printing, we need to go for a post-processing in order to remove the excess amount of material or in order to get a better surface finish. Using a metal 3D printing, directly achieving a high surface finish may be quite difficult. So this is another area where due to product requirements, it becomes difficult to adopt certain manufacturing processes. High material removal and miniaturization. When I say miniaturization, I mean fabricating micro products or having a large sample size, but I need to create some sort of micro channels, micro dimples or material removal, which is in the micro range. Now, when I say micro, I mean anything less than 1 millimeter, starting from 1 micrometer to 999 micrometer. Now, if I say I need to do a nano machining or nano fabrication, chip removal or the amount of material removal should be somewhere less than 1 micrometer, so that it can be judged as a nano machining or a micro machining, depending on the chip removal and also on the type of product that is required. Now, based on all this kind of things that we have studied, we actually can say that whether the evolution of advanced machining process is required. Yes, it is required. The advanced machining process where the workpiece hardness is irrelevant in advanced machining process. Now, irrespective of very high strength, high hardness material, advanced machining processes are able to machine to the required shape and size. Now, let us briefly discuss what are the different advanced machining processes. Now, there are different classifications. If you go through textbooks, you can find innumerable number of ways in which AMPs are being classified. However, I would simply state them as what are the different type of energies that it is being used so that we can classify them. First one is mechanical. Mechanical is basically abrasion or erosion kind of material removal. The energy is abrasive or any type of energy which can remove material by erosion or abrasion. Thermoelectric, which is mostly by melting and vaporization. We also sometimes call ablation. Chemical, which is mostly by etching. Etching is on a surface, if there is a particular acid or some kind of liquid which reacts with the material to remove and removes it or dissolves it, that is called etching. Now, under these three verticals, if we talk about mechanical, we have an abrasive jet machining where a stream of abrasives. So abrasives can be of many forms. It can be diamond abrasives, it can be alumina, or there are a lot of other abrasives. So using that abrasive jet, you actually can machine a high strength material. Now, as I speak on the AMPs, these AMPs will also have their advantages over conventional process, as well as they will have some limitations as well. Though we will not go in detail for each one with the limited time, but however, I'll just talk about a brief. Most of you may find this in any of the textbooks. Ultrasonic machining, we use some abrasives and the machining is carried out based on the ultrasonic movement of the tool, which allows the abrasives to pierce through the material, and you can generate some sort of holes or channels. Water jet machining, simply using water, the pressure and the velocity of water is controlled in such a way that you can remove material. So the good thing about using water jet is you will not find anything called as heat affected zone, which is usually present when we use processes where melting and vaporization takes place. Abrasive water jet, you are using water jet but mixed with abrasives, which aids, so which has both the combination of abrasive jet machining as well as water jet machining. So in a way, you can also say this is a hybrid type of machining where abrasive jet machining and water jet machining are being mixed. Now moving on, we have thermoelectric. As I said, electric, we are using some kind of electric field. Thermo, due to the electric field, there is a generation of some you can say the thermal energy is generated, which is helping in material removal by melting and vaporization. First one is electric discharge machining. I think this is widely known by everyone, which is EDM process. Laser beam machining, which is basically use of photons. Lasers are extensively used for machining as well as they are also used for characterization. So depending on the frequency and the wavelength of the laser, you actually can control it to either characterize samples or for machining. So higher frequency indicates higher machining. Plasma arc machining, electron beam machining. So these are electron beam, plasma arc. These are high-end machining, or the cost of developing the setup for electron beam would be very, very high. So these are very limited in select institutes only. Now moving on to chemical classification of AMPs, you have chemical machining, directly etching, where you have electrochemical machining. Again, electrochemical means based on some electric field, you are initiating some sort of etching or dissolution so that material is being removed. Now, obviously, as I said, all these processes have their merits or advantages, also have some limitations. So simultaneously, when these AMPs were being developed, there was also a field where people were starting to take advantages of two or more of these processes and coming up with something called as a hybrid machining process. For example, if I say abrasive water jet, now I can say it's a mixture of abrasive and water jet. So which comes up to be a hybrid, which is taking the advantages of water jet where no heat affected zone is there, abrasive where you can have material removal. So basically this can have a higher material removal without any heat affected zone. Again, EDM and ECM mixture, people are also using something called as ECDM, electrochemical discharge machining, where they are taking the advantages of EDM and ECM and making a new hybrid machining. So there are multiple hybrid systems that are being developed. So this is, as I said, this is an evolutionary field, and you would find that a lot of the processes or hybridizations are being done even today. So again, you can use ultrasonic with say EDM. So the tool or the workpiece, you can actually have an ultrasonic vibrations which can help in removal of the material or removal of debris after machining. So these are also possible and researchers are currently working on it. Now I will not go deep into it. Now after this, I would straight away move to what is called a miniaturization or a micro nano machining. So whenever we say micro nano machining, the difference between the conventional macro and micro nano is in the chip removal. The chip removal is micro is mostly in the dimensions of micrometer, which is somewhere between 1 micrometer to 999 micrometer. If I talk about a nano machining, anything that I'm removing in the scale of less than 1 micrometer qualifies for nano machining. Now this simple question I put forward in my next slide. So you have macro, micro and nano machining. You have a simple turning operation which we can do it in our workshop, which is called a macro turning. Now what I do is I reduce the size of the tool and the workpiece and I qualify it as micro machining. And then again, I reduce the size of tool and the workpiece and the entire setup, and I call it nano machining. I just want to know your opinion whether whatever I have said is reducing the size of the components, tool, workpiece, and other stuffs from macro to micro to nano. Does this qualify as micro machining and nano machining? Anyone from the audience can speak up. I mean, if you have any opinion on this, whatever I'm saying, is this right or do you think this is wrong? Simply reducing the size of the tool and the workpiece, can I qualify it and say that this is micro machining, this is nano machining? Anyone? Anyone? Is this whatever I'm saying, does it qualify to be a micro and a nano machining? Am I audible? The first place.
Depends upon the size we can say.
Sorry?
Depends upon the size we can say that nano and macro size.
Depends upon the size. This is macro, micro, nano. Anyone else? Anything that can come up to your mind? May be wrong, may be right. So when you say, then only some clarification can be done. Whatever I have drawn here and shown here, do you think that this is a correct way of assigning macro, micro, and nano? Or do you think there should be something else that needs to be taken into account? before we can confirm it to be micro and nano. So anyways, let me just clarify. So when I say I'm reducing the size, this does not qualify to be said as macro, micro, nano. Partly because there is a very strong term you can say which is called size effect. Now let me just give you what size effect is. When you are removing material using conventional turning, a large amount of material you can remove, right? So you are giving a particular feed and depth of cut with a particular cutting speed, you can remove large amount of material. Now in micro machining, you are reducing lesser amount of material from the material as compared to a conventional or macro turning operation. Now what happens is, if you look at the grain structure, say I'm just showing two examples. If you look at the grain structure, let me check if I can. Suppose, say in a macro turning operation, this is the amount of material you are removing. So what happens? There are multiple number of grain boundaries, multiple number of grains involved, which does not take into account the individual defects or the strength of the individual grain. So if you talk about individual grains are strong. However, when you take the grain boundaries and all other defects in the picture, this becomes much weaker. That is why when we are using a conventional macro machining or macro turning, it is very easy, and the amount of stresses developed or the cutting forces, if you measure, those are very less as compared to ideal uh, stress or strength that is required. So ideal strength, you can find out the individual what do you call the individual grain strength, and then dividing it by the amount of force that is required, you can simply find out what is the amount of stress required. Now in micro machining, say we are removing fewer number of atoms. Now what happens is, as you narrow down or reduce the amount of material to remove, this individual grain strength comes into the picture. This individual grain strength comes into the picture, and the amount of forces that is required to remove this small amount of material becomes high. I'll show another example where it is experimentally proven. So because we are reducing the size, reducing the depth of cut in a way, you can say, so say this was the depth of cut initially. If this is the depth of cut, I am simply reducing it to this one. So what, as I am reducing depth of cut, the number of defects as compared to the larger depth of cut becomes low. Lower number of defects, higher amount of strength. So therefore, the cutting forces will increase in case of micro machining. For nano machining, say we are only removing this material. So here the number of defects are very, very less. So you can consider that whatever the theoretical strength of the material is, you need to apply that amount of force in order to remove this small chunk. So when you move from macro, micro, nano, it is not only the reduction in the material removal, but it is also increase in the strength. Now, if you want to understand how this operates, it's a very old paper. I've just taken it from. So if you look at a simple tension test where you are doing your universal tensile strength, the resisting shear stress, the material shear stress is very, very less. Now when you come to turning, it's very, very higher than a tension test. Now when you start doing a precision milling, the depth of cut or the amount of material removal becomes low, the strength increases. Now let us look at this particular thing, grinding. You all know what grinding is. Using some abrasives, the abrasives is removing very low amount of material. Now you also encounter some sort of sparks. Now there is a totally different theory of cutting and thrust forces. I will not go into the detail. Now in grinding, you all know the amount of material is very low. We are only using it for a finishing operation. Now when the amount of material is low, look at the strength that is required for removing that amount of material as compared to a simple turning operation. The reason behind is, look at this. In case of grinding, we are removing some cluster of atoms where the number of defects are very low. When the number of defects are low, you have to apply very close to the theoretical shear strength of the material in order to remove that small amount of material. Whereas when you are in this multi-crystal grain, the amount of forces required are very low. That's why in turning operation, if you are removing material, it is very simple process. You don't find much difficulty. You have a tool which lasts long, which can go for some thousands of kilometers for a single material. So this is the exact difference, which is called a size effect. Increase in depth of cut, more number of defects, aiding material removal, lower amount of forces. Reducing the depth of cut, moving towards a micro and or a nano cutting zone, the number of defects reduce, more amount of individual material you have to remove, higher amount of individual grain has its strength, the theoretical strength, that amount of force is required to remove that small amount of material. So size effect is very important, and this particular thing, whatever I showed, is wrong. It all depends on the size effect. Hope this is clear to all. Now, if you are able to remove that material with any micro or nano machining process, what I forgot to tell is whatever the advanced machining process things I explained, all of them can be converted into a micro machining as well. For example, you have an EDM, which is a very large machine. It can remove a large amount of material. It can also come into the micro domain where you have a micro EDM. Now researchers are also trying to get into nano EDM where the amount of material is very low. Similarly, ECM, you have a micro ECM. Laser, you also have a laser micro machining. Apart from that, ultrasonic machining, you have ultrasonic micro machining. So all the conventional AMPs which I have explained, most of them are also available or also being developed into its own micro machining category. So it's not that we are only doing advanced machining, we're also doing advanced machining in the area of micro machining, right? Now this particular slide, I just wanted to show you that what are the different capabilities. So when I started this, someone gave a topic of this rapid prototyping, and I said about top down and bottom up. So if you look at this on the left, these are all micro machined. These dimensions are in micrometers. So if you look at this scale, it's somewhere in 100 micrometer. So this dimension would be somewhere in 30 or 40. All these small holes, maybe 30 or 40 micrometer. So these are all using top-down approach. That means you have a flat surface. You started removing material, maybe using laser, maybe using EDM, maybe using ECM, maybe using any micro process. You end up getting this sort of patterned surface. So as I said, this patterning can be used for various applications. I'll not go into the detail now. On the right, these are all bottom-up process where you can generate these pillars. You can generate this sort of circular protrusions or this conical protrusions. This can be done using physical vapor deposition, chemical vapor deposition, sol gel, additive manufacturing, 3D printing. So these are all bottom-up process which helps you to generate protrusions on the surface. Whereas top-down process where you're removing material, it helps you to develop depressions on the surface, right? So this was more about the micro machining area. Now I would like to move on to the fundamental understanding. Now, as I have simply explained the size effect, and I say that if you remove lower amount of material, you have to use higher amount of cutting forces. The reason is lower number of defects. Now, these particular things, say you have a single crystal or a polycrystal. So generally we use polycrystals. Now polycrystalline materials, you have a BCC, FCC, HCP. What happens to those? If you're going for a nano machining or micro machining, is it through normal abrasion? What happens to the grain structure? For example, a simple grinding operation, if you're considering, you know that abrasives are removing material. But what happens? Are the abrasives, do they dislodge or do they take over material or do they have an adhesive wear? For example, these are something I have taken from some literature. Now, if you look at it, these abrasives, what they would do, they would first kind of have an indent, a small indent, and then they would start removing material in the form of chip. So this is what we know about a grinding or any abrasive based material removal process. Similarly here, which is a more of an advanced finishing process, I have just taken it from one of the literature. Now what it does is you have an axial, you have a radial force, but we exactly do not know what happens to the material. If the material itself has multiple grains and we are trying to say remove using a grinding operation or an abrasive based material removal, and what happens if the abrasive somehow is falling inside a grain or between a grain boundary or some multiple grains, what happens? Understanding those aspects are very important, considering the fact that if you are not aware of what is happening in the material, you cannot go for developing your understanding and further improving the process. See, why this micro and nano machining, why the understanding is important is because once you understand the process, then only you can go for improving the process. If you do not know the physics, then how would you improve? Simply putting X and Y and doing some hit and trial, experimental trials is very difficult. Now always remember, the energy that is used, as I said, cutting forces are high in micro and nano machining. Therefore, the energy that is used in removing per amount of material is very high. Therefore, in micro and nano machining, to remove unit material, you are consuming higher amount of energy. Say it can be electrical energy or any form of energy, which is incurring a cost. So simply doing hit and trial and trying to develop the process becomes meaningless if you are consuming higher amount of energy. Understanding the physics, once the physics is completely understood, then going for developing the process is highly recommended. And also when we are doing research, it is very important that you understand what you are currently doing, the physics. So with this, there is a separate area where lot of researchers are currently moving into, which is called multi-scale modeling. Now let me give you a brief example. Most of the researchers we use, say, some commercial software such as ANSYS, Abacus, ANSYS. You have Abacus, you have COMSOL, which can do, which can optimize the process by simulation, which can give you, the cutting the stresses, the temperatures, and a lot of the stuffs. However, what it cannot do is what happens in the material at such small scales. The reason is FEM particularly uses meshes which have a limited size. Now you cannot go beyond a particular size, or the material that we consider in FEM is continuum. You cannot divide the material into individual grains. So that is one of the demerits. Now there is a scale which there is a modeling phenomena. So across scales, if you look at the system size is in meter, simulated period is in time scale. If you look both, at the very left end, you would see that it is mostly in angstrom level or nanometric level, where you use something called as ab initio and quantum mechanics. So this up to this is mostly done by computational physicists and computational chemists. But now, since everything is multidisciplinary and interdisciplinary, lot of the researchers are also moving into this area. Now, if you look at ab initio, we are only using very few number of atoms to understand very at the very fundamental level of physics we are trying to understand. It's a valence band and all other things. If you look at a molecular scale, where you actually can see, if you look at this, there's a shearing operation going on. There's a shear. So at molecular scale, you actually can look into the inside of a material, what happens. Then you have dislocation dynamics, mostly for crack propagation kind of techniques. You have this area which mostly relies on FEM based, FEM, FDM, FVM, or to some extent there are some mesoscale simulation as well. So when I say multi-scale, I mean to say I am coupling two different types of models. So I can couple an FEM with an MD. Or for example, I can couple a dislocation dynamics with ab initio. So these type of multi-scale, say, for example, if I'm using a molecular dynamics, I can actually understand what happens inside my grains. Now, if I'm doing a cutting operation and cutting operation is very long, it becomes difficult to use molecular dynamics, because as we start reducing the size, the computational power increases exponentially. So here maybe your simple 8 GB RAM would work at this. Maybe your 8 GB RAM would work. Here, if you are doing a full-fledged simulation, you need some 1000 GB of RAM in order to solve one simple problem. So that is the kind of increase in computational cost and energy if you are trying to move from to lower dimensions. Obviously, multi-scale modeling would help. Our group is currently working on MD simulations, wherein we try to explore some fundamental behavior of machining process or material science. Now we will be discussing a bit. So recently we were trying to understand nano polishing, or basically in a simple term you can say, if I have a material and I have an abrasive, how the abrasive would remove the material and what happens to the grain structure, how is it distorted, if there was some kind of some amorphous structure generated, or if the structure is FCC, how does it differ? So say for example, where is it used? If we don't have an application, there's no point of doing it. So if you look at biomedical implants where a high amount of surface finish or polished surface is required, the reason is if you do not have this kind of surface, there is always the this surface, when is rubbing against another surface, the patient would feel discomfort. Then you have high-speed rotational components, ball bearings, optical lenses and mirrors. So nanopolishing is a very important process in today's world where a very high precision as well as very high surface toughness is required. Now to understand this, we started using exploring MD simulations just to understand that if I have an abrasive and a particular material, a polycrystalline material, how does it work? So abrasive, what it will do is, first it will basically do an indent, a small indent would do, and in the vertical direction, vertical downward direction, and then horizontally, as there's an indent, which is the depth of cut, it will start moving and start removing some amount of material. Now if I go deep into it, you have the initial was, it's a 10 angstrom. So this dimension was somewhere about, I believe 120 angstrom, I think. That means 12 nanometer, somewhere in 12 or 15 nanometer. I roughly don't remember. So this is the kind of scale where MD simulation operates. You cannot go very high. If you go higher than this, the computational cost, computational power increases substantially. And also it takes higher amount of time to get results. So we do 10 angstrom depth of indentation. That means this abrasive will move 10 angstrom downwards. Now very simple video where we used something called as LAMPS. So LAMPS is an open source MD simulation software which allows you to explore this fundamental physical phenomena for any process. This is something that I am showing because we are carrying out in the field of manufacturing or material removal. However, if you are interested to work in any other field, you can explore. It's just that you need to understand how to use it and what are the different physics that is associated, what are the things you need to understand in order to start working on it. So if you look at it, this abrasive, there was an indent and this is being removed. Now if you look at this one, the right side, you see there is the green color is showing the FCC structure and the grain boundaries are amorphous. Now once it starts moving in, you see the amorphous atoms are also being taken away along with this abrasive. If you look at this red and white, so they are also being taken away. So there is a shift in the amorphous atoms that are being removed. Now if I move ahead, so this was this initial state where the indentation was completed. Now it started moving, taking into account from this particular grain, it is taking in the atoms this way. And finally, there is a material that is removed from here and taken up. So if you look at this, there's a pile up here. You can see there's a pile up here. So in actual operations, this would be removed. So you can see how material is being taken up. So we can study the grain structure. We can study how dislocations have moved. We can also study, which we have done, are the forces. Now I am just showing the cutting forces. I am not showing the indenting forces. That is why if you are doing an indentation operation, there are no forces in the X direction. There will be forces in the Z direction. There is a vertical direction. So this is the indenting part till 20 picosecond. You have the indosecond. So this is a picosecond. So this is a picosecond. Up till 20 picosecond, we have no forces since it is indenting in the vertical direction. There are no X direction forces or very minimal. Once it starts nano cutting, you see there is an increase in the amount of force. Now, we tried with 3 different velocities. These 3, because there are 3 plots, green, red and black, we are using 3 different velocities just to understand how these velocities impact the cutting forces. And there are 2 figures, one is here and one is here, to understand the extent of size of the abrasive. So when we use any nanopolishing operation, the abrasives are mixed. They can have multiple sizes. So we try to figure out if you have a very small abrasive and a large abrasive, how the cutting forces, if you look at the cutting forces here, the force would go up to 60. If you see here, the force would go up to 25. So smaller abrasives will give you lower amount of forces, so which can help you get a better finish. However, at the same time, with the lower abrasive, you will not be able to remove higher amount of material. So the time of polishing would be high for smaller abrasive, but it can give you a much better finish as compared to a higher surface. Obviously, the velocity also has its own role, which I have not shown here. Now, there are other aspects also we studied about the dislocations and how they move, though I have not shown here. Other areas, so this was more about nano polishing. One of the areas we have just worked and we have just sent it to a journal. Other areas where we are still exploring, we have explored some and we are still exploring. So this is a crater formation where we have kind of provided an energy and we try to replicate or understand in an EDM process or a laser micro machining process, if you are giving a particular input energy, how the crater will be formed. So this can be resemblance to an EDM or a kind of laser machining. So obviously the energies are quite lower as compared to the experimental values. So if you can see, there is a crater formation. If you can see, there is a crater formation here. This is the crater formation, and here if you look at the grain structure, this is 1 grain, 2 grain. So if you investigate further, and we're still investigating how this affects the amount of heat source we are applying, how is it affecting the grains, the nearby grains. So that is also something we are studying currently. Apart from that, we are also working in the area of energy storage, where we try to understand how batteries and supercapacitors behave, or if we have a particular combination of an electrolyte with an electrode, how the energy storage or what is the mechanism of energy storage we use. So this is something we also explore as part of our work here at BITS Pilani. And we also work towards developing these porous structures. So porous structures, one of the major applications of porous structures are in energy storage, where the electrodes are mostly porous. Now, what should be the amount of porosity? What should be the amount of interconnectivity of the pores? These are some things we are still exploring. So this is also carried out using lamps. So we were trying to do some quenching operation where with different quench rates, we were able to get some different pore sizes, and we are exploring how interconnectivity can be improved. So these are things that we are currently using. And with this, probably I would like to end my talk here today, where I have tried to summarize the advances in manufacturing as the title suggests, introduction, along with the research scope, that fundamentally understanding any process. So,
थैंक यू हो गया बंद कर दें टीम में
any queries from anyone?
Sir,
Yes.
sir, how lamps can help us to improve the precision? I mean, what is the exact process of that?
So lamps is not a kind of simulation procedure where it will help you to decide on the size or precision. What it can help you is to understand the fundamental physical behavior of any process. Right. So if you tell me that, sir, should I go for 10 millimeter or 15 millimeter, it will not say that this is the optimized value you should get. What it will say is, say you are having a particular, say for example, this nano polishing. Apart from that, also I have done some sort of EDM application where I can explain the material and the vaporization, what amount of material, what amount of melting and what amount of vaporization can take place if you are applying this amount of pulse energy. So that kind of things. Physical processes it can explain. It cannot give you what is, so what FEM gives. FEM can give you an optimized range, no? So if your speed, feed and cutting depth is this, you can get an optimized value. LAMPS or molecular dynamic simulation is not for that. It can help you to understand at the molecular level how your process would occur. So if you are doing your cutting operation, it can tell you if there are subsurface damages, if there are cracks, what would happen to the material. So this kind of information it can give you.
Okay, sir.
Anyone else with any queries? Okay, so just to give you a brief before the hands-on, I think Professor Tamang has already shared 3 links. One is for LAMPS, one is for Obito, and the other is for this Notepad. So we use a different version of Notepad so that it becomes easier for you to look at the code, where Mr. Ayush in the second one, who will be going to give the hands-on, will also explain how the code runs. I mean, you have an initial geometry you have made, the boundary conditions, what are the things you need to add, how do you get the output. So these things he will explain. So any queries before we close the session? Anyone?
Participant, if you have any query, you may please ask to sir.
Or if they want to contact me later, I think they can also contact me, no problem.
Yes, yes, sir. I'll share your contact detail so that yes, Jay Prakash sir is asking something. Jay Prakash sir. Okay, I think by mistakenly he has unmuted. Okay, thank you so much, sir, for your time and for sharing your valuable knowledge to the participant. Well, definitely got the insight of what the manufacturing processes is going on, and will definitely those who are early their stage in PhD or who are want to pursue their career in that advanced manufacturing field, they may got the insight of that. And in the second session will be a very interesting one that sir is going to give a demo on that software, how to run this code and everything. So thank you so much, sir.
Thank you, Professor Tamang.
Okay, sir. Sir, you will be joining at 11:30, right, sir?
I should be joining. Ayush should be taking up. So he will be giving a brief introduction, a small slide, and he will be doing hands-on. So I would join maybe around 11:30, 11:40, maybe 10 minutes late.
Okay, sir. Then if he will be continuing the session, then we'll take 5 minutes break. After that, whether it's possible to continue the session.
I think Ayush is already here.
Okay.
Ayush, can you take after 5 minutes? Can you start?
Yes, sir.
Can you start 5 minutes?
Yes, sir. It's okay. Yes, sir. I request to participants to download that software because it may take time if you have low internet connection. So please make sure all of them have downloaded the software.
Okay.
So it will be easy and fast.
Yeah, then Ayush will start the session after 10 minutes. So I request all the participants to download the software first and then get ready with that and install it. And whatever the Ayush will give the demo on that, or will follow up with our software also. Is it okay, Ayush?
Yes, sir. Yes, sir.
Okay, thank you so much. So Gaurav, can you stop the recording now?
Yes, I have stopped it.
Okay, thank you. So I request all the participants again